These notes are on the greenhouse effect, and they're going to be a little different from what we normally do in that I'm going to be bouncing back and forth between different computer simulations, some of which you saw and learned in 6th grade, but I just want to remind you of what you already know, and then some are going to be new and bring the information to a deeper high school level than a middle school level. So the first thing that we're going to look at is this sim from back in 6th grade. Hopefully you remember this. This is from the Ocean, Atmosphere, and Climate unit. And what we've got going on here, let me show you what we have set up. So this is a surface versus no surface test. And we have a solar output here. I'm going to set it to medium. We're going to have energy coming in from the sun, so that's this big arrow, and then energy leaving from the land and energy leaving from the water. And notice we've got sort of a starting temperature of -5.3 for the air. So that's really kind of what we're looking at right now. We're going to look at our air temperature. So I'm just going to go ahead and play this for a little bit, and you'll notice that that air temperature is rising. And depending on the amount of solar radiation, it will level off. You'll notice that it's slowing right now, so it does eventually level off. We can wait a second. And now you have something that is a little more balanced. It's slowing down. There's not a major change. That's, obviously how life actually works. By the way, this is in Celsius. 21 degrees Celsius is about 68 degrees Fahrenheit. And so this is how we end up with warm air. Now I'm going to pause this, and then I'm going to go to no surface, and we're going to start this over. So I'm going to take the surface out, and you'll notice the air temperature is -10 degrees. There's no surface, whether it's land or water. And we're going to play this for a little bit, and it's playing, but absolutely nothing's happening to the temperature. Okay. And so this is just a reminder of this idea that if our air is going to heat up, we actually need a surface that is going to absorb the energy from the sun and then re-radiate it back out. So put it back out into the air. And so I'm going to show you that next. Okay, so now we have another one of your 6th grade simulations. So if we play this, we've got energy coming in the form of these yellow arrows. Let me pause it. So here's an incoming yellow arrow. That is energy coming from the sun. Then we've got energy coming out from the atmosphere, some of it coming all the way from the surface of the earth, coming back out into outer space. This is the border between our atmosphere and outer space, and you'll notice right now we have a good equilibrium here with, I don't know what unit this is using, but 33 whatever going in and 33 coming out. So if you just kind of play this, you see that that's what's happening. And all of these like little, let's see if I can pause it. Yeah, and so I've got like this little circle here. All of these little circles, you can see another one here, that's where energy has hit the earth and then gotten re-radiated back out. And so that's sort of another view of what we were just seeing, and it shows how the atmosphere heats up. Now you can sort of see, and we're going to look at them in more detail in a second, but right, you can sort of see, and you may remember from 6th grade, there's these like invisible particles here, right? We now know those are molecules in our atmosphere, and we're going to look at them in a lot more detail later. We can look and see, oh look, there they all are, look at that. And we're going to look at what those do. We're going to focus specifically on carbon dioxide and methane as far as this activity goes. But if we were to, so now we know we need the surface in order to heat up. We're not going to. If we were to take all of these particles out of the atmosphere, Right now we have an average temperature of 14.9, and now we're going to play this. And notice that the temperature is actually falling. And so without all of these particles, Earth's surface, or let's just say Earth's atmosphere, is too cold for us to live in. And so that's a really important concept that I hope you do remember from 6th grade, is that this idea of a greenhouse effect, and we call it a greenhouse effect because it's like a greenhouse. And I'm going to show you in a second a little more about how a greenhouse works. But if you consider this boundary between outer space and the atmosphere like the glass of a greenhouse, without this heating up of our atmosphere, it's just too cold for us to live, and life does not proceed the way it has on Earth today. So we need this atmosphere, and then the idea here is that Earth's air heats up, and I did put that in quotes because heats up is a little bit of a judgment call, like heats up compared to what, but Earth's air heats up when solar radiation is absorbed by Earth's surface and then re-radiated back out into the atmosphere, which is what we saw. That's why we need the surface. And so approximately 50% of incoming solar radiation is absorbed into the surface, and then some of that is radiated back out into the atmosphere in an attempt to reach thermal equilibrium. In other words, if the surface is too warm, it's going to re-radiate some of that heat back out so that the surface and the air can be in equilibrium with each other. That's what's going on there. However, we now look and we can see if we were to increase these greenhouse gases, and this is nothing you don't already know, because again, this goes back to 6th grade, now that temperature is going to go up. And you'll notice what's happening is, and I don't think I'm going to be clever enough to actually be able to pause it perfectly, but when some of this energy hits a greenhouse gas molecule, that energy then gets scattered back into the atmosphere. Now realistically, and I'm going to show you this on a different sim, realistically that energy could get scattered in any direction. It could get redirected in any direction, but normally this energy is leaving the atmosphere. And instead of leaving the atmosphere, it now has a chance of staying in the atmosphere and going in any different direction. So I'll let that play for a second and you can kind of see that happen. We can even slow it down a little. Maybe that will help. And then you can really see that, oh yeah, here's some incoming energy and now it's going back towards Earth's surface instead of going out into the atmosphere. And you can see the global average temperature is still increasing. This is a new sim from the 8th grade Amplify, so you won't have seen this one. And it deals with the nature of light waves, and so I want to quickly go through a couple of main concepts here. So light, hopefully, as you know, is energy, right? Energy is the stuff that makes things move or change. And here I've got the sunlight, and I'm going to turn on the sunlight, and then I can tap this beam to see what kinds of light are in the sunlight. So hopefully at some point you learned about the electromagnetic spectrum, but that is essentially a way of saying all the different types of light. So going from the highest energy, lowest wavelength light, we have gamma rays up at the top. Those are extreme cancer-causing rays. Those are what are in nuclear bombs. All the way down to radio waves down here. Radio waves are very low energy, long wavelength rays of light. And that's what, like our cell phone communications and Wi-Fi internet, those all rely on radio waves. Radio waves are not sound waves. So what a radio, like in your car, does is it changes the light waves, the radio light waves, into sound waves. Speakers do that. Totally other story. We're not going to deal with that. But then in the middle here we have our visible light. So with all the colors of light, right, you know that we learned earlier this year that white light is a combination of all colors of light. And just to review what we did already know, like if we put this plant here, that green light gets reflected, and that's the light we end up seeing. So hopefully you remember that. I'm actually going to put the plant back here for a second, and then put the glass here. And I can, again, check out this beam and see, okay, yep, there's all my light. And then here, you'll notice I'm missing the infrared. Infrared is heat. So that's staying in the glass to warm up the glass, that then warms up the air. That's that re-radiation, just like on Earth. And that's what warms the air of the greenhouse. Interestingly enough, ultraviolet, which is our cancer-causing rays, so skin cancer, also gets absorbed into the glass, so it kind of helps protect the plants a little. But all of that visible light that the plants need in order to grow gets transmitted through the glass, so the plants have them. So this shows too that, and now hang on, let me take this glass away. When light hits an object, three things can happen. So I'm going to tap on each of these types of light, or light rays, we'll say. And I want you just to pause the video, look, and see if you can figure out what are the three things that light can do when it interacts with an object. So I'll give you one. This green shows that light can be reflected off the object. Okay, so figure out what the other two are. Go ahead and pause the video. So hopefully you got that light could be reflected, which I told you, or absorbed, or transmitted through objects. So if we go back to the sim, we see the green light is reflected. The radio is what we'd call transmitted. It's why we use radio waves for communications, because they actually go through, they transmit through a lot of objects. And then everything else is absorbed into this plant. And then if we inspect the plant a little closer, we see there's actually a lot of stuff going on. There's some damage to the plant, there's some photosynthesis, see more leaves, there's some warming up of the plant, and all of that has to do with light that's been absorbed. So light that is reflected or transmitted through objects does not affect the plant any. It's the light that's absorbed that affects objects. So the damage is due to like the UV light, and also probably in this case the gamma rays and X-rays. The photosynthesis is due to all of the colors of visible light except green. The warmth is due to the infrared that's right here. One thing I do want you to notice is that the infrared waves, which is the heat, and that's really important because that's what we're talking about when we're talking about heating, is lower energy and longer wavelength than the visible light. And that's really, really important for what I'm about to show you. So keep that in mind. This image here now is an image of all of the light that comes from the sun that we just saw. So, right, these should all look familiar, and they're in order from gamma all the way down to radio. And what actually reaches Earth's surface and what gets either bounced back or absorbed in the upper atmosphere. So the gamma rays and X-rays, which again are huge cancer-causing rays, luckily for us, don't actually reach down to where we are down here. I don't know how big, I mean, this is kind of clearly not to scale. But the ultraviolet and visible absolutely do, and those get absorbed into the Earth's surface. And then that's what gets re-radiated back out. But it's re-radiated as infrared light. So in other words, this light, once it's absorbed and re-radiated, has lost some energy and become infrared light. All of this is essentially the same type of light, it's just how much energy it has. And it makes sense that as things are absorbed and then re-radiated, they're going to lose some energy. And so that's where you're getting a lot of the heat from. It's not necessarily heat coming directly from the sun that then, quote, bounces off the Earth's surface. It's ultraviolet and visible being absorbed into the Earth's surface and then re-radiated out as infrared light. So when we're looking back at this sim, these bouncing out are not exactly the same kind of energy going in as going out. I mean, it is, if you want to say it's electromagnetic radiation, but a lot of this coming in is visible light, and then what it bounces back as is infrared light. And so that's a big difference in our understanding, and that's kind of a deeper level at this point. This is another sim that comes from a completely different website, but it's showing a very similar thing. Let me pause it. Okay, the yellow is the sunlight photon coming in. A photon is essentially for right now, we're going to call it a packet of light. And then the red one is the infrared photon. So this is actually showing what I was just telling you, that what's coming in are these sunlight photons. Now, those could be visible, those could be ultraviolet. The vast majority are visible. Some are, in fact, infrared. The sun absolutely gives that off. Some are going to be radio waves, some are going to be microwaves. But the point is, once they're re-radiated back out from Earth, they're infrared. So just notice that for a second. Oops, wrong one. So a couple of technical difficulties there. So you should be noticing that we've got sunlight photons coming in and infrared photons coming out of the Earth. Now we're going to look at why. So here we have yet another simulation. We're going to just focus on the infrared photons because those are the ones that are being radiated back out, which are the ones that are warming our atmosphere. And I want you to notice here we have CH4, which is methane. So if we turn this on, let's give it, and notice every so often, now some of the photons pass through, but every so often the methane absorbs the infrared photon and radiates it back off in a different direction. And this is what I was saying in the earlier sim where, actually let me get to that earlier sim for you. That's what I was saying in this sim, that there's light coming in and it always seems to bounce right back out to Earth. So like these that hit, oh no, that one actually went out in the other direction. But we do sort of think of it as they keep bouncing back to Earth, whereas in fact what could be happening is it could be going in any direction, but the point is it's not going back out into space. If you consider outer space over here and say this being the surface of the Earth where the infrared photons are coming. And so that's going to happen if you're using CO2 or methane or water, so like water vapor, notice that that happens there as well, but not nitrogen and not oxygen. And so just take a second and notice what is the chemical difference between methane, carbon dioxide, and water versus nitrogen and oxygen. Remembering, of course, that the vast majority of our atmosphere is nitrogen and oxygen. And then these are some of the other things that are thrown in there. So hopefully you noticed that these are all compounds. They're made of different elements. And because of that, their atoms can have different interactions than when you've just got the nitrogen atoms or the oxygen atoms. And if you want more information on why they can behave differently, I'm happy to talk to you after class. But what you need to know now is it's that atomic molecular level here, right? We're bringing that back in, where because these are compounds, they are able to absorb the energy and then bounce it back in a different direction, which is what leads to the heating of our atmosphere. And that's why the more CO2 you get and the more methane you get, right? You go back to the food choices. Cows are a huge supplier of methane, and methane is a much stronger greenhouse gas than carbon dioxide, the more methane and CO2 you're putting into the atmosphere. Quite frankly, the more water vapor too. But we're not dumping tons and tons of water vapor into the atmosphere that's not already there. The more heating you're going to get. So this is a lot with a lot of different kind of moving pictures. So please make sure you write down and ask your questions in class. Have a good night.